Okay, if P then Q, if that then, if not Q then not P. Okay, well, it's like people might recognize that this is actually the contrapositive. Equivalence is just one way to do that. So the task is to prove that this expression is a tautology. Well, we know this is a tautology, so that will be that will guarantee that we will be able to simplify it down to just a tautology, that letter T we used for that. And it's some people suggested that at some point we can use the law of the contrapositive. Well, that's what we are proving here, so that would be a bit of a circular proof. But okay, this is a logical expression, and we need to prove this is a tautology. And we need to use the laws of propositional logic. So here they are, and the names and the corresponding laws. So whenever you see one side, you can replace it with the other side. And these are the names that you need to put for each step where you use it. So it's clear that what happened. And it's very important to make just one, apply just one law at a time. If you do two at the same time, well, it's, first of all, there's not enough detail, so you lose marks in the exam. But also, probably more important, if that when you do two steps at the same time, you are more likely to make a mistake. So yeah, it's a win-win if you make just one law per one step. So how to do this one? Well, first of all, we have a couple of conditionals. So let's just work inside the parentheses. So we can say by representing conditionals. Okay, we can write if P then Q. Well, that's the same as not P or Q. Okay, well, let's not do this one, but we can, well, sort of do this one as well. So this will be, yeah, it's not Q or not P. Okay, so well, the next thing is that I realize that, well, I have double negation here. So by double negation, I can simplify then. So I have not P or Q, then Q or not P. So now again, representing conditional, because now I have this big conditional. By big, I mean that's at the top of the hierarchy. By representing conditional. Okay, so we have, it's not true that not P or Q or Q or not P. Right. So this one, I have a disjunction, a logical OR, and it's negated. So I need to use De Morgan's rule. So that will be, well, the negation goes inside, so it's not P. That turns around, and not Q or Q or not P. Okay, well, again, by double negation, I have P and not Q, or Q or not P. So right, so what we can realize here that well, this is an OR and this is an OR as well. So actually these parentheses group these two together, but you know, we don't have to. So because it is an associative operation, so I can just say that P and not Q, or Q or not P. So that's, well, that looks good, because you know, we have P inside and we have not P outside, and we have not Q inside and we have Q outside. So actually either way it will work. However, again, we want to make sure that by associativity, now let's just make it like that, that I will put the parentheses here. So these steps of removing the parentheses and putting the parentheses, that looks like, you know, it's like, oh, it's so obvious. Well, you know, nothing is obvious in mathematics, as you have to justify. Oops, okay, we have enough room here. So what's the next step? Well, this is distributivity. So by distributivity, well, that will be okay, I'm inside that parenthesis, so it's P or Q, P or Q, and not Q or Q, and okay, I have this parenthesis, or not P. So by negation law, that's a strange name, but what we have here is that this is P or Q, and I use letter T for tautology, because this is always true regardless what's the value of Q. So I have that. And now I know that, well, I'm saying that P or Q, or something which is always true, so the truth value of this logical end only depends on this one, and that's called identity law. Okay, so that will be P or Q, or not P. However, it's or, so by associativity, it's a long word, I can say that it's P or Q, or not P. Oh, we see that P and not P are the same there, same expression. But okay, let's just move this there, and that can be done by commutativity, because logical OR is commutative, so it's P or not P or Q. So then again, by associativity, I can say that this is P or not P or Q, which, well, I'm running out of room here, but again, by identity, it's actually by negation. I mean, the names are not particularly exciting here, but that's what's used in the table, so this is how I can identify it. So this would be something always true or Q. And now, well, by universal bound, from there, I have just T. Okay, that's a tautology. Because something which is always true or Q, well, it does not depend on Q. That's just a tautology. Okay, so that finishes this proof. It was a tautology, so we managed to get down to just saying T. It's very important, just one law at a time, each step. Okay, because that's why it is readable. Even it feels like that, oh yeah, it's like, it's so obvious. But, you know, this exercise is also about communicating the thinking process, and that requires writing it down in detail. Okay, so that concludes the proof by using logical equivalences.